Okay, so welcome back. At the end of last lecture, I'd started talking about John Napier and his discovery of logarithms. So I wanted to kind of continue that discussion because it's interesting. So John Napier was a Scottish aristocrat, lived from 1550 to 1617. And he devoted 20 years of his life to the construction of logarithms. So the work in which he does this is originally the title is in Latin. Translated title is The Construction of the Wonderful Canon of Logarithms. So construction of the wonderful canon of logarithms. And if you hadn't thought much previously about where logarithms came from or kind of how they were developed, it might come as somewhat of a surprise to you that they were developed prior to the discovery of calculus. But as we kind of went into this discussion last time, once you actually write out exactly what he was talking about when he was constructing this, you see where looking at it from a modern viewpoint, it becomes clear immediately what is happening here, and where that particular form of the logarithm that he uses is. So what he calls the logarithm is actually it's typically called now the Napier logarithm. So when he says logarithm of x, as I mentioned last time, what he actually is doing is 10 to the 7th log base 1 over e, or e is Euler's number, the base of the natural log, of x over 10 to the 7th. So this is the Napier log. This is nap log x. So this is the Napier log. And you can check out the Wikipedia article on the Napier log to see exactly where these things came from. To show you why we get log of 1 over e here, the construction that I mentioned last time is the following. So imagine that we're looking at the plane here, and on the plane, imagine I'm starting at the point -1 here. So I have initialized some point here, some particle that's at -1. So particle P is at x equals -1 when t, we're thinking of as a time parameter, is equal to 0. So we have some initial time t when this particle is sitting at -1. What is the idea? The idea is that P moves, so here's my P. P moves at a speed, so we'll say moves toward the origin. So it's moving in this direction, okay, at a speed proportional to its distance to the origin. So this is the key thing. Okay. This is the key property that really brings in what ends up being a log involving this number, which is called Euler's number, even though obviously Napier was dealing with this thing before Euler. But it's called Euler's number for, well, I'll get to that when we talk about Euler. But this, basically the form of this showing up as log base 1 over e here comes exactly from this description. Once you say that this motion is occurring at a speed proportional to its distance to the origin, that seals your fate. Okay, and the reason that seals your fate has to do with has to do with differential equations. So this is very basic differential equation stuff that basically says the second you specify this condition, there's only one thing that satisfies that. And the thing that satisfies that involves this E. Okay, so before I go on, so first of all, when we write, so a note on notation, this was not Napier's notation. So this is modern notation. When you write log sub a of x, we read that as logarithm base a of x. Okay, that's what this means. Okay, E is Euler's number. Again, Euler wasn't alive when this was going on, so it wasn't called Euler's number then. E is Euler's number, which is also called the base of the natural logarithm. What is the natural logarithm? The natural log is the log base E of x. And in modern notation, this is written as ln of x. Although I call this modern notation, but really this is modern notation for Calc 1 through 3, and that's about it. Because once your math studies progress past kind of the 100 and 200 level math courses, this morphs into, we don't use ln anymore, we just say log x. And when we say log x, we mean the natural log, because the natural log is by far, it's by far the most, natural choice of a logarithm. I mean, even in Napier's original construction, there's a log base 1 over e, which through log rules is related in a really easy way to the log base e. Now, you might have seen log x before, written to mean the log base 10, right? So log base 10 of x is also a common log that occurs, and I'm going to talk specifically about what's nice about the log base 10. So I'll talk about that in a little bit, but kind of the most two commonly used logs are the natural log and the log base 10. The most commonly used by far is the natural log, and so in higher math, when you see log x, that usually means natural log. When I say log x, I will specify here in a second exactly what I mean by that. Okay, so this is just kind of some background here, and I'll talk more about some of these quantities later as we go forward, especially once we get to talking about Euler, because he proves some specific things about some of these quantities, and that's why, that's one of the reasons why this E is named after Euler. Of course, this is an irrational number. It's also transcendental, just like pi, so it has an infinite decimal expansion, never repeats. So E is 2.71828459. That's the first zero of it, and so on. This is Euler's number. It's 2.718 and so on. Okay. All right. Okay, so going back to this construction. So the idea is, and I'm going to make a bigger picture here. So let's say here's 0, here's my origin. Here is -1. Here's my particle P. The motion is occurring in this direction. Okay, and so what is the idea? So at time t equals 0, I'm at -1, moving in this direction toward the origin. Now, the idea is that for any distance d, right, so for any distance d, so specify a distance. Okay, so I specify a distance d. Now, this distance is d. The idea is for any distance d, there is some time, I think last time I called it big T, for which the particle is that distance from the origin. So the particle P is exactly d distance to the origin. This is easy to see. So in this setting, this particle is moving toward the origin at some speed, right, that is proportional to its distance. Once we have this motion occurring, if I specify some distance to the origin, it's got to pass through that point on its way to the origin. And so at some time t, it passes exactly through that point, whatever time t that is. So we say that this t is the logarithm of d. And we write that t is equal to log d. Now, written in this way for us, here's the big note that is very important for the rest of this discussion today. So note, today, that means today in lecture, not today as in like in modern times. So today in lecture, when we say, or when we write log x, we mean log base 1 over e of x. Okay. All right. Now let's use a little bit of machinery that we've already developed here to see what it is that's going on. So in that same picture, let me bring that back for a second. So in this same picture, I have some things occurring. So first of all, if I write x of t, this is my position or distance from 0. Okay, this is my displacement from 0, if you like. Okay, thus my position when t is equal to 0 is -1. Right? And I'm told that speed is proportional to distance from 0. Right? That was the key defining thing about what's going on here. Well, in terms of what we know about position functions, if you start out with a function that denotes position, how do you get at its velocity, right? Of course, the magnitude of its velocity is its speed, but how do you get to velocity, right? How fast something is moving? Well, you take a derivative. How do you get to acceleration? You would take 2 derivatives, right? But I'm happy to stop here for now. So saying that speed is proportional to its distance from 0 means that x prime of t, this is velocity or speed, if we're happy that this has already been normalized, right? So this is already, I've already taken absolute value here. Then this is saying that x prime of t is equal to some constant c times the distance. It is proportional. So here's speed, or here's velocity in this case. This is proportional to the distance from 0, so where this c is my proportionality constant. All right. Okay. And so specifically, if we take my proportionality constant to be, we'll say, -1 here, or we'll say that it's proportional with respect to 1, but we put a minus sign here for convenience. So take c equal to -1 here. Okay, so really I've added this sign for convenience here since I'm starting on the left side, since I'm starting at -1 here. So using this, I have the equation x prime of t is minus x of t. and I have the initial condition x of 0 is equal to minus 1. Now, as I mentioned last time, this is technically an IVP, or an initial value problem. This has a solution that is x of t is minus e to the minus t. And you can check that it actually satisfies that, right? In fact, let's check real quick. X prime of t, this is minus e to the minus t times minus 1, right? That's the derivative of this thing. But that is minus 1 times minus e to the minus t, that's just x. So this is minus x of t. So indeed, this satisfies that equation. And if if I plug in 0 here, I get minus 1. So good to go. Okay, so this is it. All right. Now, again, using our modern machinery, then if I wanted to look at log of x, or log of x of t here, right? That's log of my distance. Right, then I'm taking log of, and this is, we'll say the natural log, right? Log base e. So log base e of minus e to the minus t here. What's another way of writing this out? Well, this is to say that minus log d here. So minus log base e of d, that's my distance, right? X of t is my distance here. Okay. Well, this is the same thing as writing it as log base 1 over e of d. Okay, so what this is saying here is that this t is equal to log base 1 over e of d. And so when I had that fact starred on the previous page, that is where this comes from. Okay, so when I say log x for the rest of this discussion today, I mean the log base 1 over e of x. Okay. All right. Okay, and so as it's written here, this logarithm of some d, this distance, is the time t at which this particle is exactly that distance specified from the origin. Okay, so first question. How did Napier... So first of all, the book that I mentioned at the very beginning of today's lecture, Construction of the Wonderful Canon of Logarithms. So this contained essentially a computation of a bunch of logarithms. So the question is, how did Napier actually compute these? So how did he compute the log of d? Right? Because, as I mentioned in the last lecture, whenever you have encountered logarithms in the past, it's typically something you do in the context of, you have a calculator right in front of you, and you are using that calculator to compute these logs. Now, if you were students many years ago, if you were students like 50 plus years ago, when there were no calculators that could easily compute logarithms, you would have used what are called log tables. Right, you would have used log tables to actually write out some of these logarithms and compute with them. And so, but I mean, how are those log tables generated? Right? How did the first person who discovered logarithms actually compute with them? So it's very tricky. And as I said, Napier himself spent like 20 years of his life coming up with this. All right, so the immediate answer to how he was computed, he made use of 3 important facts. So he made use of 3 facts, okay, which I'm going to outline now as they're listed in your textbook. So here are the 3 facts. So the first one is when z is very small, log of 1 minus z is approximately z. So I'm going to write that one down because that's fairly short. So first fact, when z is small, the log of 1 minus z is approximately z. Conversely, if you replace z with 1 minus z, this is equivalent, or I shouldn't say conversely, but equivalently, I can say that if I replace z with 1 minus z, this is 1 minus, well, I'm just going to work it out here. How about this? But what is this? 1 minus 1 is 0 minus minus z. So equivalently, log of z, if z is small, is approximately 1 minus z. Okay. Okay. So both of these things hold true here. Okay. So this is the first fact that he made use of, and I'm going to show exactly how he made use of that. All right. So the second fact, okay, if I look at natural number powers of 1 minus 10 to the minus m, where m is some natural number, these are easy to calculate. Okay. So for instance, it says take s to be 1 minus 10 to the minus m. Okay. Then s squared is s times 1 minus 10 to the minus m, which is s minus s, this is just distributing, right? S minus s over 10 to the m. Now think about what that means, and I'm going to give some examples here that are listed out. Think about what that means for a second. So if s is 1 minus 10 to the minus m, then to compute s squared, I just take s and I subtract from it s divided by 10 to the m. Why is that easy? Because s divided by 10 to the m, that's just me taking s and moving the decimal, right? This is just me moving the decimal to the left m places. So it's just me shifting my digits, my decimal around, right, in base 10. And similarly, I can continue this pattern. So s cubed is s squared minus s squared over 10 to the m. And I can compute s squared easily from this previous step. So this gives me an iterative process where it's actually not that bad to compute these powers. So it's always just a matter of shifting the decimal point m places and subtracting. Thus, here's some examples that Napier computes explicitly. So 1 minus 10 to the minus 5, right? Well, 10 to the minus 5, you know what that is. That's 0.00001. So 1 minus 0.00001 is 0.99999, and then nothing but zeros after, right? Okay, so if I wanted to compute this thing squared, using this trick up here, all I have to do is take the number I started with, right, this 0.99999 and then a bunch of zeros, and subtract from it that exact same number, but shifted m places. The decimal is shifted m places to the left. So I take the number I started with, 0.999999, and then, or sorry, 99999 and then a bunch of zeros, minus 0.000009999 and then a bunch of zeros, right? So I took this number I started with and shifted the decimal point to the left 5 places, and I subtracted. So this gives me 0.9999800000100, and then nothing but zeros. Okay, so I continue. Cubing this, I take the previous number, right, that I've worked through here. So cubing this, I take the previous number that I worked through, and I subtract from it that previous number, shifted again, the decimal, 5 places to the left. And I get another number here. And I can continue. I can do this as much as I want to for higher and higher powers. Okay, so this isn't so bad. I can keep going as long as I want to, right, as long as I'm feeling like it. And the third rule, near 1, the log is smooth, and linear interpolations give excellent approximations to it. Okay, so then if we consider the line segment, right, joining two nearby points, Right? That is very close to how the log behaves. That's what is meant by these linear interpolations. Give excellent approximations to it. So then seeing where the line goes close enough basically tells me what the value of the log is. Okay. So how can I use those three properties together? So 2 and 3 as explained right in the book. Okay. So how can I use these three facts to compute logs? All right, so the idea is so near -1, Napier's particle is moving at about 1 unit per second. Okay, and we can assume through that first fact that the log of d is equal to 1 minus d for d equal to 1 minus 10 to the minus fifth, which is 0.99999. Okay. So Napier uses 2 as before, the example I showed you with 1 minus 10 to the 5, to compute d squared, d cubed, d to the 4th, and so on, all the way up to d to the 50. Okay. And once he's computed d to the 50, so he finds that d to the 50, using this same process we saw, that wasn't that hard, but it took some, some elbow grease. It took some tedious computations to compute this. But again, he had 20 years to do this, so, plenty of time. He finds that d to the 50 is 0.999500, and then some other stuff, so 1225. Okay. All right. Now, how does that help? Okay. Thus, how does this help me? All right. Thus, the log of 0.999500125, right? That's this d to the 50. So that's log of d to the 50. Well, this is 50 times log d. All right. This is 50 times log d. Why? This is one of the logarithm properties, right, that you might remember. So log d, as we saw up here, is approximately this thing, right? So log d is approximately 0.99999, right? So this is 50 times 0.99999. Okay. So then, what's the next step? So Napier uses linear interpolation. That is, he looks on the line nearby to find an accurate value for log u, or for log 0.9995. Oh. All right. Where does this come from? From here. All right. Okay. So the value that gets computed from here tells me roughly what this is, right? It's close enough. It's an approximation. Okay. Now, how does that help? So call this quantity U. So U is 0.9995. All right, how does that help? So next, Napier does the following, again using this same property that it's easy to compute the powers of things that look like this. So Napier computes, so just like he computed D and all those powers, since he now has U, he computes U, U squared, U cubed, all the way up to, let's say, U to the 20. Okay. He finds, after he's done this computation, that U to the 20 is equal to 0.990047358. Okay. Again, using interpolation, so using linear interpolation, he finds accurate values for log of 0.99. Where does that come from? Here. All right. Call that W. So call W 0.99. So at this point, he's very accurate. Okay. These values he's computing are very accurate. So now, what is the idea? So big question. For instance, how would Napier compute, for example, log of some specific value, like log of 1/2? How would he compute that? Okay, because you might say, what's going on here? How is he computing? Like, what's he doing finding this U and this W using this process? How's this helping him at all? Okay, well, the answer is as follows. So for A between 1 and 20, and B between, say, 1 and 68, okay, Napier computes U to the A times W to the B. How does this help? First of all, how many of these is he having to do? So there's 20 different powers of U here and 68 powers of B. This is how many lines, right? How many points are in this? This is 1,380 points, right? Again, 20 years. All right, so he had 20 years to do this. So calculating this product 1,380 times, not too tall an order for him. Okay, so this gives him, first of all, it gives values in the range that he needs to compute this. What do I mean? So notice. Okay, so notice the following: that U to the 19 times W to the 68. What is this? Well, you couldn't notice this, but I'm telling you that after Napier did this computation, U to the 19 times W to the 68, which you could check with a computer if you wanted to, is 0.5001100996. And U to the 20 w to the 68 is equal to 0.499860940. And so it now becomes clear what it is I was doing, right? You might say, why do you only go up to 20? Why do you go all the way up to 68 here? So this is not how Napier did it going forward. Going forward, he was looking for values that gave him exactly something like this. Why? What do you notice? Well, u to the 19 times w to the 68 is equal to something a little bit more than 1/2. So this is strictly bigger than 1/2. Then 1/2 is strictly bigger than u to the 20 times w to the 68, which is slightly less than 1/2. But they're very close to 1/2, right? And so here is where I use linear interpolation again to give me exactly what I want. What do I do here? So noting this, then if m is equal to the log of u to the 19 w to the 68 minus log of u to the 20 w to the 68 over u to the 19 w to the 68 minus u to the 20 w to the 68. What is this? Well, then m is the slope of the line joining those two given points, right? Points in question. So then using linear interpolation again here, what does this mean? It means that log of 1/2, 1/2 being squeezed by these two quantities, right? This is approximately log of u to the 20 w to the 68 plus 1/2 minus u to the 20 w to the 68 times m, this slope. Okay. And so what this is here, using log rules here, cheating, right? This is 20 log u plus 68 log w. Both of these quantities I've already computed. Minus computing this quantity is no problem. 0.000278. So Napier's already computed all these quantities. I use log rules here to split this up in this way. Log u and log w are already computed. Going through this entire process, what do I get? 0.693147. It turns out this is accurate to all those decimal places. This is accurate to 6 decimal places. Now you might say, wow, that is a ton of work just to compute the log of 1/2. But once you have the log of 1/2, it becomes a lot easier to compute some of these, right? And this is how computing logarithms work. Now I'm going to mention some specific techniques, or, well, very briefly, here in a second for log base 10 that works as well, that kind of simplifies some of the computations with logs that need to be done. But moving on, so like how does this help me find a general log? So how does this help further computation? Well, for further computation, note that if t is between 0 and 1/2, right, and I want to compute log t, How can I do that? Well, if I'm trying to compute log t, then log t I can find by finding some integer, say k, such that 1/2 is strictly less than 2 to the k times t, which is strictly less than 1. If I can find an integer such that this is the case, then I can solve this no problem. How? Well, if I can find such an integer, then I just look at log t. Using linear interpolation here, this is log of 2 to the k times t plus k log of 1/2, but I've already computed log of 1/2. Right, I know what this integer is, and computing log 2 is easy because it's minus the log of 1/2. And so this becomes k times log of 2 plus log t, right, plus k log of 1/2. And so this is no problem here, right? So I can compute log of 2 easily because it's just minus the log of 1/2 here. Okay, so this is kind of the idea here. All right. Okay. So this meant that Napier could construct log tables that computed a number of these logarithm values for various values, and use some of the properties of logarithms to make some of the computations not so terrible once you had this table in front of you. So the next person to mention, inevitably, is Henry Briggs, who actually traveled and discussed logarithms at length with Napier, and additionally convinced Napier of investigating log base 10. So convinced Napier that log base 10 of x was interesting and had several applications. So in this vein, Henry Briggs is the one who came up with the terms, so defined the terms mantissa and characteristic. So what are these things? These are terms that apply to logarithms base 10. What is the idea to logarithms base 10? So in 1624, Briggs published a log table for log base 10 of x. Okay. The notion of a mantissa is the following. Basically, if you have numbers, say 173, and this is base 10, 17.3, 1.73, 0.173, 0.0173. All of these are said to have the same mantissa. Okay, so all of these have the same mantissa. This is found in the log table. But you know that the logarithm of these things is not the same. So what is the difference between, say, the log of 173 and log of 0.173? Well, this is where characteristic comes in. So the characteristic is found just by looking at these things. What's the characteristic? The characteristic is basically how the decimal moves. So it's how the decimal moves. So for instance, you would have the characteristics of these starting here would be 2, and then 1, and then 0, and then -1, and then -2. So you see exactly what it is. How far do I have to move the decimal here for it to only have a single number to the left of the decimal? 1, 2 to the left. So that has characteristic 2. Okay, here I would have to move it 1 to the left, so that has characteristic 1. Here I don't have to move it at all, so that has characteristic 0. Here I would have to move it to the right 1, so that's characteristic -1. Here I'd have to move it to the right 2, so that's characteristic -2. Okay. So you could, using these quantities, you could very easily compute with log base 10. So why is log base 10 interesting? You might have guessed already. It's because the number system we use is base 10, right? So so that's why log base 10 is nice in this way. Okay. So similarly, and you might want to think about this for a second, if we had say a sexagesimal system like the Babylonians, you might want to investigate log base 60, right? Okay, so what were the immediate applications of logarithms? They're great for dealing with certain types of data, right? Like cheating a little bit, looking forward, thinking of the logarithm as a function of x. We know one of the key important properties of the logarithm is that the logarithm of x, if you think about its growth, it grows extremely slowly. Right? So the logarithm base 10 of 1000 is 3. Right? Think about plugging 1000 into just a polynomial, right? Like the function f of x is equal to x squared. If you plug 1000 into that, you get 1000 times 1000, so that's already 1,000,000. Okay, and that's still a polynomial. That's just a degree 2 polynomial. So that thing, compared to the things that grow really fast, like exponential functions, that thing doesn't even grow that fast. And already, if you plug 1000 into it, you get 1,000,000, right? Which is well, depending on your definition, is a fairly large number. But you plug that same quantity into the log base 10 of x, and you get 3, right? You plug 1,000,000 into the log base 10 of x, you get 6. Right? You plug 1,000,000,000 in, you get 9. So this thing grows really, really, really slowly. And so the logarithm is great for dealing with gigantic quantities, of course. And the algebraic properties of the logarithm are great for various reasons. But specifically, some of the computations that were being done at the time, some of the data that was being first compiled at the time were actually, it was convenient to use logarithms to talk about these things. So even Kepler, that hopefully I'll get to by the end of lecture today, made use of this fact. So the development of logarithms is very important. Briggs was important because he was the one who convinced everyone that log base 10 was something to look at, and he basically kind of expanded on Napier's work. And I mean, he did this, in concert with Napier. He met with Napier several times and worked through this stuff. Okay, so the last thing I wanted to talk about in my Renaissance mathematics list, I said there were 4 main things, right? The third one was the development of logarithm. So the last is mechanics and astronomy. So, mathematically speaking, there's maybe not as much math going on here compared to the first three topics, but it's hard to pass through this era of mathematics and not mention some of these big names, because while maybe mathematically they didn't contribute in a huge amount, there's some side things to say, and also it's just hard to pass through this era and not mention some of the big names, even if they weren't great mathematical innovators. Mechanics and astronomy. The first name to mention is Copernicus. So you've no doubt heard of Nicholas Copernicus. So he was Polish. He was born in 1473 and died in 1543. He a popular understanding is that Copernicus was the first to suggest the heliocentric model, right? So he's kind of the father of modern astronomy in suggesting the heliocentric model. But of course, we know, as we've mentioned before, that Aristarchus was actually the first to seriously consider a heliocentric model. So there was one more example of a Greek thinker previously that had mentioned a heliocentric model but hadn't really worked out anything or didn't really say much. But Aristarchus, and in fact Copernicus himself actually credited Aristarchus with the heliocentric model. So heliocentric model he was a big proponent of. So recall Aristarchus. Okay, you can go back and read his entry to remember exactly what Aristarchus did, but Aristarchus was kind of the earliest serious proponent of the heliocentric model. So Copernicus, it should be said, you can read the works of Copernicus. The thing that I'll say is that what was his most important contribution was not that his model correctly predicted anything, because it didn't. There were a lot of problems with it. But he correctly noted that a move to a heliocentric model vastly simplified some of the things that had to occur to explain what was going on. So his model still used epicycles. And his model wasn't super duper accurate as far as meshing with the data. There's probably a good reason for that, namely being that he still used Ptolemy's data. Okay, we'll see this is kind of the big key distinguishing feature of what Copernicus did versus what Kepler would eventually succeed in doing. So I'm going to stop here for now and start with this during the next lecture. So I'll pick up exactly here. All right. So anyway, I will catch you later.